So here's a simple friction problem. Let's say we had a 50 kilogram box sitting on an inclined at some angle theta. The incline is steel and the box is steel, so that determines what the two surfaces are, and we can now read the mu sub k's or mu sub s's as appropriate from the table in your book. So there's two questions. First of all, um, find the friction if theta is equal to 20 degrees, and is it static or kinetic? And second, at what angle for the incline will uh, m, which represents the box, begin to slide? And so you know from your experience in life that if you did this experiment and you set theta to 0, as you increased the angle of the incline, at first the box wouldn't slide, but there would come an angle at which it would. So I'm going to do number 2 first. And so here's the free body diagram. I'm now going to tilt my coordinates so that the x positive direction points down slope and y is upwards and perpendicular to the surface of the incline. And so if I do that, I've got three forces acting on the body. I've got the gravitational force downward. Um, I've got the normal force of the incline acting on little m, and I've got up the plane, I've got the frictional force resisting any tendency that the mass has to slide down. So I do know that the sum of these three forces, S sub g vector plus n vector plus f vector, is equal to the mass times the acceleration. But the acceleration is equal to 0, the vector acceleration, because it's just about to slide. So now I can write the x and y components of this equation, and if I do, if I look at f sub g, these red vectors now represent me taking the vertical f sub g vector and getting a component perpendicular to the ramp and one that's parallel to the ramp. And this right here is mg sine theta. This angle and this angle are the same. So mg sine theta represents the both the magnitude and the direction in the x-axis system that I've chosen, minus f. F is up the plane anti-parallel to this vector, and that's going to be equal to 0, which means the frictional force is mg sine theta. And in the y direction, well, these two forces have to cancel each other. So n minus mg cosine theta, so the magnitude of this perpendicular component of f sub g perpendicular to the ramp is mg cosine theta. That has to be 0, which means n is mg cosine theta. Remember that I said when an object is on a ramp, the normal force becomes less. Well, cosine theta is going to make it less than mg, which it would have if theta was equal to 0. So now I can put an expression together for the frictional force. Frictional force is mu sub s times n. Mu sub s times n now represents the maximum frictional force possible. So that's going to be mu sub s times n, which is mg cosine theta. And in that case, I can use the x equation now to set mg sine theta, which f is equal to mu sub s times mg cosine theta, which I've just gotten up here. So I can solve this equation, simplify it by dividing by cosine. The mg's cancel out on both sides. And so what I'm left with is tan theta is equal to mu sub s. And this gives me an angle. I can solve using the inverse tangent. And if I use the static coefficient of friction for steel on steel, which is 0.8. That would be the inverse tangent of 0.8, which is about 39 degrees, 38.7. So in other words, if theta is, for this situation, if theta is um, um, less than 38.7, let's say 39 degrees, M will not move. It will just begin to move at 39 degrees, and then for angles larger than that, it will now begin to slide down the ramp. So that tells me that for the first part, since I have an angle of 20 degrees, that I haven't gotten to the slide condition yet, because 20 degrees is less than this critical slipping angle. And so therefore I can go back to the F equals mg sine theta, and I can conclude that the frictional force is simply mg sine theta, which is 50 kilograms, using easy numbers here. No, 50 kilograms times 9.8 meters per second, excuse me, using the real value of g, times the sine of 20 degrees. It's 170 newtons. So 170 newtons would be the frictional force in that situation.